Hi, I hope you're doing fine. This is my final late submission. Assignment 9 Proximal Policy Optimization is as a kind of algorithm. It uses a policy grading method with better stability and performance. So the in this process in this assignment, we are applying PPO on playing this game of Atari game Pong. Yeah. So let me run everything, and in the beginning we install some the Atari environment, given the version and room license, useful packages, and we import our useful packages as well. We enable GPU so that make things happen faster. Then we download the some utils codes and parallel environment code. So some codes from GitHub to help us, these helper functions or utility functions that help us with better process. And the environment is defined here. It's defined as this one. And the states are the number of observations, and actions are given here. So you can see there's 6 different actions, and we can read more about that here. So it includes no operation, fire, right fire, and left fire. And to process each, so to reduce the computation, we are resizing the frame from 210 times 160 to 80 by 80 square, and then make it a grayscale from RGB to grayscale, and then remove the background color and this graphical stuff to just make it work faster. So it looks like this from this. And here we define the policy, and still for making things faster and easier here, we're just choosing 2 actions, so it's a binary decision making, and out of the 6 actions we are only working on right fire and left fire from the available actions set of 6, and the policy would uh, be selected by a neural network architecture with 2 convolutional layers and 2 linear layers, followed ending with sigmoid, and we pass these here, except for the last layer. The remaining are ReLU as usual, and we set the hyperparameters. 1 to the e negative 4 is the learning rate, and the number of actions for right is 4 and for left is 5. And we select the policy, move it to the GPU, and optimizers Adam in this case, given it the learning rate and the policy parameters. So what we need to know about the PPO algorithm is the way it processes. So there is an L clip that is the clipped surrogate loss function. So it tries to basically stabilize the process of learning by minimizing the amount of change. So it takes the minimum value, the average, but average of some parameters, including the minimum value of 2 main. So here, 2 main parts. One is the the what is it called, the ratio function that we're going to talk about later, times the advantage. And another one is the clipped version of that ratio advantage, regarding the epsilon value that we discuss later. So ratio is what the term that is trying to make it stabilize better by dividing the dividing the policy given current policy by the old policy, and for each uh, given action for state. So it's like this is a ratio of the advantage we are giving it. And the advantage is the difference between Q value, Q table in that state in action. And its difference with the value of that state. So it's like how much advantage we can get by taking that action, but not add it entirely mm, to the previous to update the values, but multiply it by a ratio to make things go more slowly and more stable. And so what is the clipped value? Clipped is like we give the same ratio, but instead of passing the ratio, multiplying the ratio directly to the advantage, we kind of clip it regarding the epsilon value by 1 minus epsilon and 1 plus epsilon. So it's like clipping it from two sides and just taking a part in the center. And depending on what the value of epsilon would be, epsilon is a hyperparameter, and it can be something between 0 and 1. And it means that we do not allow, so if it's a small value like 0. 0.1, we do not allow policy to change by a lot. But if it's a big value, it means that there is a chance that the policy may have high variance. Um, So in exercise one, what we want to do is to add a line to calculate the ratio. So we implement this line here, current policy divided by old policy. And then add a line to clip the ratio between 1 minus epsilon, 1 plus epsilon. To do this, we can get help from the clamp function from PyTorch that does the exact same thing that we want to. And so here is the function that calculates this clipped surrogate loss here. It takes in the policy, the old probabilities, the states, actions, rewards as usual, in the discount value, epsilon, and beta, which I'm not sure. Okay, so beta is later used for another term that is not defined here, but we're adding to do some entropy regularization to. So later we will discuss this. But we are aware of the remaining things. These are old terminologies. And to calculate the discounted reward, the discount would be discounts to the the length of reward, or what, like how much has it been passed, and then the reward is whatever a given reward is multiplied by the discount. And the future reward would be all the rewards um, going backward, and then calculate the mm, accumulative accumulative sum of it. I'm not sure if I'm using the right word in English, but and then it's also normalized by mean and standard deviation. So it's the reward normalized. So here we also get the action by so it's like converting the action to a torch tensor. Old probabilities, this is just conversion. This is also conversion. New probabilities would be um, convert states to probability and gets the IDs but torch that were. And then here is what we change what we were supposed to do. Calculate the ratio, which is the new probability divided by old probabilities. Oh, sorry, by P. So let me just. Yeah, I did everything right. Okay. And then to do the clipping, we use the torch.clamp function, pass it the ratio, and we can then clip it from 1 minus epsilon and 1 plus epsilon. This is how we use it. And then we calculate the clip surrogate as given up there in the formula, that is the minimum value of ratio multiplied by reward and clip multiplied by reward as well. So here was the discussion that we had advantage here, which is different than reward, that we should use in the formula. But according to the paper linked here, linked in the top of the course, there are different methods to apply this, so reward is also used. And regarding that paper, I'm sorry, I moved a lot. Regarding that paper, we can use reward instead of advantage, it seems like. So we, instead of advantage, we multiply ratio by reward and the clipped ratio by rewards, and then choose the minimum value between these two, so it shows how small the change would be. If the clipped value is a smaller, let's choose that one. Otherwise, so let's it's a good idea to increase the reward and try to make it the maximum. But here we are choosing the minimum so that the change is very slight and the system stays stable and doesn't fluctuate a lot. And here is an entropy calculation that uses the beta hyperparameter. It's it is an terminology used to encourage exploration. And at the end, we return the average of, so it's the E and the formula of the clipped surrogate loss plus this beta times entropy, which is going to help with exploration. So these are some parameters to define: 250 episodes, 0.99 discount rate, zero point 0.2 epsilon, 0.01 beta, and Tmax is the maximum number of steps, time steps, and how many times the neural network is going to be trained to apply this stochastic gradient descent to update the policy. And here it is running because I ran it kind of late. And so how it works, we define the environment uh, and we use parallel environments from the functions loaded to increase the speed and get the best use of the resources available. And we want to calculate the rewards so that we show how it changes along the time. So initially it's zero, it's empty, and then we want to add values to it later. So this TQDM is something to make it look this nice that the percentages are feeling. This is how we use it so that we can see the training process as explained here. And what happens in here is that we calculate all of these old probabilities, states, actions, and rewards by the collect trajectory, function that I guess should be inside the yeah, it's inside the utils that we loaded. And then the total, so it takes in the environment, the policy, and maximum number of time steps. And the total reward would be the sum of all the rewards taken from this. And then we want to do the update on the policy. So we apply a loop to the number for the number of epochs we defined up there, to calculate the loss by clipped surrogate loss function, giving all of the parameters we discussed. And then we initialize we zero gradient, do the gradients zero on the optimizer, and do a loss.backward function to go backward and update the weights of the neural network. Then here is where the update happens, to save memory, we just delete loss. And then this repeats multiple times to update, waits for a little bit, and then move forward to change the epsilon by a decaying factor, make it one step smaller, and beta as well. In the average reward, we are adding the average of the total reward we had up there, um, and add it to the list so that later we can plot that. And so these all happens in the range of episode. I didn't see this. So it each all of these things happen in one episode, and then it goes back again. And this is just for displaying the results after a while. So it's like after each 20% is showing us some rewards across CP. Why CPU? Oh, it shouldn't be. Okay. It's just it's just what we printed here. But this is the rewards, average reward. So it should get better, but in the beginning, because of the high exploration rate, it gets a little bit worse. Then it tries to act better and better, and we should wait until it fails completely. But because we don't have time, I'm going to just explain the rest, and we can come back and see. So here we plot the mean reward. So we expect it to move down, as we discussed here, if we are training right. And the next one deals with the rendering of gameplay from a trained policy. So we can here see how this works, but I guess there was another part. Yeah. Okay, so in exercise 2, I didn't discuss this. That we wanted to set the optimizer gradients to 0, so this is one of our tasks that I didn't mention, and we wanted to backpropagate the loss. This is another thing that we needed to do. And so it keeps training on the GPU. It takes about 25 minutes, and it's currently on 70%, but fortunately at the end it will show some animation here. Thank you. Have a great night.